Hey everybody, it's Mr. Oaks. Different entrance this time. So today I'm going to talk about, in this video, the difference between a linear function and a nonlinear function. Now, the basic thing is to realize that when we have a linear function, it's a line. It literally has the word line in it. So a linear function is a function that is a straight line. Okay? Doesn't curve, doesn't bend, isn't points all over the place. It's flat out a straight line. Nonlinear is a function that's not a line. Non-linear. Now the ways we're going to normally see this, we're going to usually see this as a graph, as a table, or as an equation. And in each case, we're going to have something different we're looking for. Now, the first thing I have here is a group of graphs. And I'm doing that first because figuring out whether something is linear or nonlinear is kind of easy when you can see it. You can see whether it's a straight line. You can see whether it's not a straight line. So looking at these, when I look at this first one, that's a straight line. That's linear. I mean, it doesn't get much simpler than that. All the rest of these are nonlinear. And we can see because right here, this is a parabola. It's curved. It's not a straight line. So, nonlinear. Here, this is an absolute value function. It's nonlinear because even though we have a straight line, it bends and it goes off in a different direction. It's not linear because it's not a continuous straight line. It changes. So again, non-linear. This last one, don't see that often. Most of the time, I teach 8th grade, we won't see something like this, but we'll see it as just points. But sometimes you'll see a graph like this. This is not linear because it's broken up. There's no continuous slope, rate of change. It changes. It might be going up, but each time it looks like steps. So this is also nonlinear. So as I was saying, when we look at a graph, graphs, they're not that difficult to tell whether they're linear or nonlinear. Because basically what you're doing is looking at it and saying, is that a line? Yeah. A straight line, it's linear. No, it's going off, it curves or it goes off in weird directions. It's nonlinear. Okay. Okay. So, then we come across tables. Now, tables require us to do a little bit more work. Now, the thing that we need to do in order to figure out whether a table represents a linear function is to see, does it have a constant rate of change? Basically, does it have a slope that is consistent? It doesn't change every single time. Now, you got to be careful sometimes with these tables because sometimes the values will jump around and you'll be like, well, it's not consistent. The trick is to look at the difference between the x values, compare it with the y values, and see when you set up your ratio, do you have the same number each time? So in my first one up here, I have this table 0, 1, 1, 4, 2, 7, 4, 13. So when I look, I notice going from 0 to 1, I'm going up by 1. From 1 to 2, still going up by 1. From 2 to 4, however, I'm going up by 2. I'm not going to automatically be like, whoa, well, this is not a function because I still have to look at my y's. Maybe it's still consistent. So I'm going to look. 1 to 4, that increases by 3. 4 to 7, again, increases by 3. 7 to 13 goes up by 6. Again, it changes. But I'm going to set up my ratios. I'm going to go and set up my ratios as y over x. And if I get the same value each time I set up that ratio, then this is a linear function because it has a constant rate of change. So we have 3 over 1, which gives us 3. Again, we have another 3 over 1, which again gives us 3. And then we have 6 over 2, which when we do that division, still gives us 3. So this is okay. I'm getting the same rate of change every single time. Therefore, this represents a linear function. Then I'm going to look at this second one here. 0, 0, 1, 1, 2, 4, 3, 9. So again, I'm going to look. 0, 1. 1 to 2, again, is a 1. 2 to 3 is a 1. So that time, that's consistent. We're getting the same number every single time. Cool, that's looking okay. On the bottom, the changes in the y's. 0 to 1 is 1. 1 to 4 is 3. 4 to 9 is 5. Now if I do my comparison again, I do my y over x. It's weird writing it that way. But I've got 1 over 1, which is 1. Then I have 3 over 1. That's 3. So that's different. Let me make that a little darker. And then this one, 5 over 1, that's 5. So I've got different rates of change every single time. This is nonlinear. All right, it's going to change. It's going to curve as if I was to graph it. And that's another way I could actually check these tables, is see, if I graph it, do I have a straight line? Yes? No. So the last thing, equations. Now, the biggest thing with equations, I'm going to move this up a little bit. Is that if it's linear, I can rewrite the equation so that it can be in the form y equals mx plus b. Okay. Now, these are both examples of linear equations. This one's nice. It's already written in y equals mx plus b form, or slope-intercept form. We see that its slope is 3, its y-intercept is 2. So, pretty, okay. I have a constant slope, so it's linear. This one is in standard form. And so when we look at it at first, we might be like, oh, that's not in y equals mx plus b form, so I guess it's not linear. But the big thing is go and look at it and say, can I rearrange this in such a way that I now have it in y equals mx plus b form? So when I look at this, the first thing I'm going to do is I'm going to move my 4x to the other side. I'm going to subtract 4x from both sides. And now I have 2y equals negative 4x plus 7. It's kind of looking like it's in y equals mx plus b form. So I want my y to be just y, so I'm going to divide everything by 2. And when I do that, I run out of room. But I get y equals negative 2x plus 7 over 2. It doesn't matter that I have a fraction for my y-intercept. What matters is that overall, this is in y equals mx plus b form. I have a constant slope, and that's what we're looking for when we want to see if it's linear. Does it have a constant? Does it have a constant slope, or does it change? Nonlinear, the best thing to do is to kind of look and see, does it look like it can be fixed and put into, not really fixed, but can it be put into y equals mx plus b form? And I have here a couple of different examples of nonlinear equations. The one you're probably going to mostly run into is something in the form y equals x squared. So some type of what we call quadratic equation. Y equals x squared plus 2x plus 1. Y equals 3x squared minus 4x plus 7. Things like that. Those are going to be giving us a parabola, so it's curving, therefore it's nonlinear. Here we have the x variable is in the denominator. Again, this is going to cause our graph to curve. There's no way I can actually rewrite this equation to put it in y equals mx plus b form. So if my x variable is in the denominator, my equation is nonlinear. Right here, x squared plus 4y equals 15. That's actually the equation for a circle. And as we know, a circle, not a straight line, so nonlinear. Square roots, majority of the time, nonlinear. You might have to go and plug in a few numbers to see, well, does it, maybe it actually works out nicely. It depends on where the square root is. If the variable is under the square root, it's probably nonlinear. And lastly, we have here where the x is actually the exponent. So this will cause will cause a curve that will make it nonlinear. So these are just examples of nonlinear equations, and linear, we're going to be able to rewrite it into the form y equals mx plus b. I hope this video was helpful for you to figure out the difference between a linear and nonlinear functions. Please like and subscribe, and make sure to comment. Let me know if there was something in the video that you didn't understand, and I'll try to fix it in a future video. Or maybe there's something that I didn't go over and you're like, hey, well, what about this? Again, I'll make a video. All right? Hey, I'm here for you. Everybody have a good one. I look forward to helping you some more. Have a good one. Bye.